इससे आस्क कर लेंगे,
हाँ
सब पूछ लेंगे अगर डाउट होगा तो।
नहीं, एब्सोल्युटली एब्सोल्युटली, बिकॉज एसेंशियली नहीं पूछोगे तो नुकसान तुम्हारा ही होगा, राइट? बिकॉज आंसर पता है तो ऐसा नहीं है कि आंसर नहीं पता, अगर आंसर नहीं पता तो ढूंढेंगे, तो इसलिए just ask, even if it's like the tiniest thing, छोटी छोटी चीजें भी, it's important to have clear in your head. Okay, very good. So let's review what we did in the last class. We ended on the first law of thermodynamics. We ended on the first law of thermodynamics. Can somebody remind me what the first law of thermodynamics talks about?
Conservation of energy.
Oh, very nice. It's talking about conservation of energy. How does it talk about conservation of energy? It talks about conservation of energy in the way when it says that if I put heat inside a system, I have a system here, A, let's call this. I'm putting some heat inside the system, delta Q. What will happen to the system? Well, some of the heat will be used in increasing the internal energy, and some of the heat will be used in doing work. And for gas, we essentially figured out that delta V is nothing but P delta V. Delta W is nothing but P delta V, where P is the pressure and V is the volume of the gas, right? So essentially, अगर मैं कोई भी heat provide कर रहा हूँ, तो वो उसकी internal energy increase कर रही है and P delta V increase कर रही है. अच्छा, when I say that the internal energy is increasing, what essentially do I mean? I mean, so this is essentially in delta W is.
Energy.
I'm sorry?
Kinetic and potential.
Yes, so it's going into the kinetic energy and the potential energy. But here, since we're talking about only ideal gases, so essentially things which obey PV is equal to nRT. Since we're talking about ideal gases, you remember in the simulation I showed yesterday, all of these different balls were just coming and hitting each other and going away. So there wasn't any potential energy, there was only kinetic energy. So all the internal energy, when it comes to an ideal gas, it goes into increasing its internal energy, into its kinetic energy. And obviously temperature is just the average of kinetic energy, is proportional to the average of kinetic energy. So if the kinetic energy is going up, the pressure is also going up. So this the temperature is also going up. So the internal energy going up means that the temperature will go up. Or if the internal energy comes down, means temperature will come down. So internal energy has something to do with the temperature. And we had learned about something else. How does energy and temperature relate with each other? Does anybody remember how does, if we have a body A and if I'm putting in some energy delta Q, तो उसका कितना जो उसका temperature जो rise करता है, what is the quantity that defines that?
Heat capacity.
Heat capacity, exactly. So rather than heat capacity, we can talk about specific heat. Specific heat जिसको हम C से कहते थे, which was essentially equal to the amount of energy I'm putting in per unit mass, so mass, specific energy, and molar specific energy, specific heat we talked about initially, and delta T here. So the energy that I'm putting in, how is it going into the material here? My delta Q, which is essentially my delta U, right? Because this delta Q denotes all the energy that is being absorbed by A. So all this energy that is being absorbed by A is essentially increasing its internal energy. So this delta Q is essentially my delta U. Because here we are only talking about increasing. Work done के बारे में बात नहीं कर रहा, pressure के बारे में बात नहीं कर रहा है, वो कैसे हो रहा है, volume के बारे में बात चेंज नहीं कर रहे, हम खाली temperature के बारे में बात कर रहे हैं यहाँ पे. So my delta delta u, so essentially from here is just c m delta t. This is essentially how much heat I need to put in, and अगर मुझे heat per unit mass पता चल गया तो which I can call, अगर per unit mass अगर कोई चीज पता चल जाती है, so that's just good to know, right? I know this per unit mass, internal energy अगर मैं इतना provide करूंगा, so वो उसका temperature कितना पड़ेगा, right? So obviously we talked about first law of thermodynamics. We also talked about the zeroth law of thermodynamics.
Sir, how did you make it equal this del Q and del U?
Yes. Here, when we are talking about specific heat, जब हम specific heat define कर रहे थे, हम कह रहे थे कि अगर उसका definition जो था specific heat का was essentially if I put in some energy into a system, its temperature goes up. And how much does it per degree Celsius increase of temperature that I want to do? How much energy would I need to put in per unit mass? Obviously, is called the specific heat. But now realize when one is defining this as energy input, this, or where is this energy going? This energy is not going in work done. This energy is going in just increasing the internal energy. So that is why here, when one is talking about specific heat, one is actually talking about the internal energy going up rather than the work done. So डेल्टा क्यू तुम प्रोवाइड कर रहे हो, बस उस डेल्टा क्यू से जो इंक्रीज कर रहा है वो खाली डेल्टा यू इंक्रीज कर रहा है. वी आर नॉट टॉकिंग अबाउट हाउ दिस इंक्रीजेस.
Okay,
Make
okay,
sense?
sir.
So that is why this is actually a hidden delta u. This is not actually delta q. This is a hidden delta u. So yeah, this is actually delta u, not delta q. Okay. Yes. So specific heat. So हमने कुछ questions भी किए थे. But okay. Yes. Zeroth law of thermodynamics. What was zeroth law of thermodynamics talking about? कोई याद दिला सकता है?
Equilibrium.
Yes, it was talking about equilibrium points, and it was actually necessary to define temperature. So zeroth law is talking about temperature. First law is talking about conservation of energy, and then we'll come to the second law, third law. We'll come to all of those things later. But अभी तक हमने यहीं तक किया. Lovely. Now let's delve deeper inside this equation. Delta Q is equal to delta U plus P delta V. Now let's think about this delta U again. And let's think about it in a particular context, in a context of an ideal gas. Okay. So my delta U I have defined as C, where C is the specific heat, and delta T. If I'm putting in some energy, my temperature of the body is going up, and by how much amount it is going up, it is dependent on the specific heat. But when one talks about an ideal gas, things become very tricky. Because why does that happen? That is because in an ideal gas, I can vary this C as much as I want. I'll show you examples. So for example, let's take case one. The first case, let's think about a piston wala setup. We have a gas inside a cylinder, and we have a piston which is sitting on this gas. So now what I do is I very, very sharply, I very, very quickly just decrease the volume slightly. उसको अंदर थोड़ा push कर दिया, but very quickly. When I do this very quickly, there was no time for heat to be exchanged, right? So there was no time for the internal energy to go up, but my volume changed. So in my equation, PV is equal to nRT. My volume changed. My volume actually went down. So what else can change? My pressure can change and my temperature can change. Let's say my temperature change some delta T. So what is my C now? My C in this case, when delta T, this is just zero. So my C is actually zero in this case. So minimum value of C that can happen. This is a situation that can happen. You can just quickly decrease the volume, uh, and without it changing the internal energy. Uh, so what will happen? My specific heat is essentially zero in this case. We can talk about the other extreme also. We can talk actually about three different things altogether. Now think about the same system. Think about this uh, gas in a piston, this gas in a cylinder with the piston on top of it. And now what I do is I put some energy in it. So I heat it up. I heat up the gas. Now, two things can happen, right? One thing is essentially my temperature goes up and my volume also can go up, right? But how much the temperature goes up and how much the volume goes up, those are dependent on how much my internal energy is actually my heat that I'm providing inside is going inside the internal energy or it's going inside the work done. If my volume is going up, I am doing work. If my temperature is going up, I'm increasing the internal energy. So how much does one happen? So three things can happen, right? One thing is most of my uh, energy heat that I put in actually goes into the work done. Most of my heat goes into the work done, and some amount of heat goes into increasing the temperature. So this is actually smaller, right? So C here is, which is delta U by delta T in this case. My delta T U is small and my temperature increase. It's also you can have some increase in temperature. So this can be greater than zero. But what can also happen is that the volume expands so much that my temperature actually goes down. So my delta T can also be negative. So in that case, my C is actually negative. And what also can happen is that my delta V is exactly so that my there is no change in temperature, which we will call an isothermal expansion. It can expand in a way that my temperature does not change. In that case, if my temperature does not change, your C is delta U by delta T. And if my temperature does not change, this is delta U by zero, which is infinity. So you realize that the value of the specific heat can actually go from any negative number to any positive number up to infinity. So an ideal gas is essentially a toy model which can be used very, very well in all kinds of situations. So your specific heat can vary from wherever to wherever. Does that make sense?
Yes, sir. But can you please explain that how will it be possible that this isothermal expansion you're providing heat, but but still the stuff substance is not heating?
But the construction is not heating.
No,
Well,
no, the system.
huh?
I'm saying you're providing heat, but still the system is not getting heated up.
Yes, the system is not. So how this can happen is if see all it's increasing in volume, right? Why is it increasing in volume? It is increasing in volume because it wants to compensate for the external pressure that so it is doing work against the external pressure. So to increase, so now how much it increases depends on the external factor. It does not depend on internal factor. If the external factor is such that you increase the volume so much that your actual temperature goes down. That can also happen. In that case, you'll have negative C.
Okay, okay, sir. Got it, sir.
Oh, sorry. Apparently my internet is being weird. Sorry about that. Yes. So where was I? Yes. So think about it again. We have a piston here. You have some gas here. Now you have so what do you mean by work being done on the piston? Where is the work being done? If the gas is expanding, what is the gas doing the work against? अगर अंदर की गैस एक्सपैंड कर रही है, so it is doing work on something. What is it doing work on? Is it doing work on the piston?
Yes, sir.
But the piston is massless. So my work done, which is essentially equal to force times displacement, my force, which is mass times acceleration, my mass is zero. It's a massless piston. So my work done on the piston will actually be zero. So what is the work done against? And this is the crucial point. The work done is against the external pressure. You have some external pressure here. So what it is doing, it's increasing its volume to come to the same pressure, because for equilibrium to happen, the outer pressure and the internal pressure has to be the same, right? The internal pressure has to be exactly the same as the external pressure for an equilibrium to happen. So to reach that equilibrium, one can one can expand a lot if the external pressure is small. One can expand very small if one can also contract if the external pressure is higher than the internal pressure. All of those things can happen. So the point is that the specific heat of a gas depends on what condition you are calculating the specific heat in. उसका कोई particular specific heat नहीं होता है. Gas can have an ideal gas can have whatever specific heat you want. As I showed you in the case one, when I said कि you suddenly compress it so that there is no heat that goes inside. When you suddenly do this, the pressure inside goes up and the temperature also goes up. Because you're decreasing the volume, and in that case my temperature goes up, so I have some temperature, so my C, which is delta U by delta T, my delta the energy I put in, this is zero, so my specific heat is zero. My case 2 was essentially if I heat this up. My case 2, case 3, and case 4 is talking about when you're heating up the gas itself. When you're heating up the gas, the energy is going into the internal energy and some work is being done. Now, the external pressure will define how much work is done, right? Because work done, as we know, is PdV. So pressure is important to work done. What is the pressure? So what is the external pressure? It will go on ahead and match and increase in the volume. Now it can increase in the volume so much that the temperature that the increase in temperature there is some increase in temperature, as in some energy is going into delta U. So my delta Q heat that I'm putting in, delta U plus delta W. Yes, some heat is going inside delta U and the temperature is also going up. So both my delta T is positive and my delta Q is positive. Is positive. This would mean that C is positive. What else can happen is my delta T is negative and my delta Q, because I'm putting in some heat, is positive. So in this case, my C is actually negative. What else I can do is I can match it exactly such that my delta T is equal to 0. In this case, C goes to infinity. C goes as infinity. C goes to infinity. Make sense? So
Yes, sir.
essentially, here we are only talking about how the specific heat of an ideal gas can be anything you want. Okay.
So,
Hmm.
sir, please explain case third again.
Case third is when the external pressure, मान लो external pressure बहुत कम है, internal pressure बहुत ज़्यादा है. So what happens is that when the gas will expand, it will expand so much that the temper, एक जैसे ही कोई गैस एक्सपैंड करती है उसका टेम्परेचर नीचे जाता है, राइट? Because PV is equal to nRT. If the pressure is the same, if you increase the volume, my temperature has to go down, right? So essentially, my so to for any gas to expand, your temperature has to go down. So essentially, it's cooling, and if it cools so much that the temperature actually जो initially temperature था उससे ज़्यादा कम हो गया. So my delta T, which is T final minus T initial. So if my T final is actually smaller than T initial, so my delta T is actually negative. So in this case, my specific heat will also be negative. Make sense?
Yes, sir.
So
Lovely.
that is why we write V is directly proportional to T and not T is directly proportional to V.
Yes, because then it depends on the pressure as well, because pressure can also change.
Okay, okay, sir.
Okay. So in a gas, you can define two kinds of specific heat. अभी तक we were talking, so what is essentially happening? You have a system A, इसका pressure is changing, इसका volume is changing, इसका temperature is changing, right? You have specific heat. Now what you can do is, well, temperature constant रख के तो हमने already देख लिया. My specific heat, अगर temperature constant है, तो that is some whatever energy I put in divided by 0 is infinity. ये तो हमने already देख लिया. Two more things that we can do is we can put pressure as a constant and volume as a constant, right? So that will lead us to specific heat at constant volume, जिसको हम डिनोट करेंगे CV से, and specific heat at constant pressure, जिसको हम डिनोट करेंगे CP से. Okay.
Yes, sir.
So so ये जो प्रोसेस हो रहा है इसमें प्रेशर कांस्टेंट है, ये जो प्रोसेस हो रहा है इसमें वॉल्यूम कांस्टेंट है. Now can you tell me what is there a relation between CP and CV, in the sense CP और CP में से CV में से कौन सा बड़ा होना चाहिए?
CP.
Why? Why should CP be greater than CV?
Because the volume can increase for CP and not for CV.
Lovely. So essentially what you're saying is, if we come back to our original equation, P delta V, if my pressure is constant, let's see, my pressure is constant, so my volume is changing, right? My volume changes, so my energy that I put in goes both into work being done and increasing the temperature or increasing the internal energy. But if my volume is constant, all my heat is actually going into increasing the internal energy. So it is actually more difficult to increase. So in the sense that you'll have to put in more energy to increase the temperature at a constant pressure. So that is why my Cp will be greater than Cv. Does that make sense?
Yes, sir.
That's a completely an argument based theorem that Cp will be greater than Cv. Simply because एक केस में दोनों में जा रहा है, दूसरे केस में एक में ही जा रहा है, जो भी मैं डेल्टा क्यू डाल रहा हूँ। जब एक बार डिवाइड होगा तो ऑब्वियसली उसमें कम जाएगा, और टेम्परेचर बढ़ाने के लिए कम यूज होगा, एंड डेल्टा वी बढ़ाने के लिए भी यूज हो सकता है, बिकॉज okay, so my Cp will always be greater than Cv. Lovely. Now let's try to find a relationship between Cp and Cv. Okay, so let's start again with our beautiful equation P delta V. Now let's first think about if my volume is constant. If my volume is constant, this would mean that delta V is 0. This would mean that delta Q is just equal to delta U, right?
Yes, sir.
So what is CV? CV is just delta Q by delta T at constant volume, which is essentially equal to delta U by delta T. It's at constant volume, uh, which is, yeah, so yeah, that is what your CV in this case is, when my volume is a constant. Now, when my pressure is a constant, what happens? Well, my delta Q in this case is just my delta U plus P delta V. So what is CP? Well, CP is delta Q by delta T at constant volume, which is equal to delta U by delta T at a constant, at a constant pressure, obviously because we're talking about constant pressures, constant pressure plus P delta V by delta T at constant pressure. Lovely. Um, okay. Can somebody think what we should do now? If you want to get a relationship between CP and CV, we have one relate. We know what CV is. We know what CP is. This is delta U here.
We can
How do we
subtract,
combine these two equations?
subtract equations.
Huh?
We can subtract,
We can subtract the two. What would that do? That would,
cancel out this del u by t and del u by t. Oh, no, no,
yes,
no. Sorry.
yes. Because why? Because these things, do they depend on the volume? Do they depend on the pressure? No, they do not. Absolutely, they simply do not depend on the volume, because delta U in the case of an ideal gas, it just depends on the temperature.
So that means the subscript of v and p will not make.
Matter in this case, yes. So that is why when we subtract Cp minus Cv, we know that Cp is greater than Cv. Because so this will be a positive number. We can figure that out. So these two, okay, I'll just write this down. Delta U by delta T at constant pressure plus whatever pressure you have, delta V by delta T at constant pressure minus delta U by delta T at constant volume. So these two terms essentially cancel out, because it doesn't matter if it's dependent on pressure. Both of them are independent of pressure and volume, so it doesn't matter. So you can cancel these two out. So this is just equal to P delta V by delta T given at a constant pressure. Now, so this is essentially what CV minus CV is. Right? Now let's think about the ideal gas case, where my where my equation of state is given by PV is equal to nRT. Okay. So if my pressure is constant, so P and I change some volume should be equal to nR delta T. Correct?
Yes, sir.
So this would mean that P delta V by delta T, and since this is at constant pressure, there's a constant pressure here, should be equal to nR. We can substitute this thing here because the left hand side is exactly the same. And what we get is Cp minus Cv is equal to number of moles by R. And if I want to consider n is equal to 1, so my Cp minus Cv is just equal to R. What is R here? This is the gas constant, right?
Yes, sir.
Somebody remembers the value of this gas constant?
8.314 by joule per mole per Kelvin.
Wow. Okay. Yeah, something like that. You'll always get this questions like this in your exam. Okay. यहाँ तक everything is clear, right?
Yes, sir.
What are we trying to do? We are trying to divide whatever energy I'm putting in into the internal energy and the work done. Internal energy means increasing the temperature, and work done means changing the pressure or the volume. Okay. This will be true only in the case of an ideal gas. If there is a more complicated situation than that, then my how I write down the internal energy will still be C delta T, but my C will be a more complicated creature. It won't be just a constant anymore. I mean, it won't be a number anymore. It will turn out to be a matrix, which is a fascinating field in itself. Anywho, okay, so can we do a question? Okay, this is simple. Let's do the simple question. Uh, the difference between two specific heats of a gas is 5 into 10 to the power 3 joules per kilogram per Kelvin, and the ratio of the specific heats is 1.6. Find the two specific heats. Yes. So the difference between, so you have two specific heats, you know the difference, you know the ratios, find what the two are. Rather than being a question on thermodynamics, the question on mathematics. Lol. Any thoughts on this?
Yes, sir.
Tell me.
So it is that Cp minus Cv equals nr is given, and the ratio between Cp and Cv is given. So basically a linear equation.
Lovely. So essentially, what do you have to do here? What you're given is the difference in specific heat. So Cp minus Cv, because Cp is greater than Cv, is equal to 5 into 10 to the power 3, 5,000. And the ratio is Cp divided by Cv, Cv. Again, because Cp is greater than Cv, so this has to be, and it's greater than 1. So Cp has to be in the numerator, is equal to 1.6. This implies Cp is equal to 1.6 Cv. Let's put it back inside. What do we have? You have 1.6 Cv minus Cv is equal to 5 into 10 is power 3, which is zero point 0.6 Cv is equal to 5 into 10 is power 3. So Cv is just 5 into 10 to the power 4 divided by 6, which is something 0 0.8. So 8 into 10 is power 5. 10 is power 5. Uh, Whatever units. Yeah. What are the units? बता सकते हैं? Joules per
सर वही
kilo
होगा
per
जो
Kelvin. Lovely. And
सर
you put and
सर
you just put this back inside here. So essentially multiply this by 1.6. 1.6 into 8 into that is your CP.
सर what is that ratio?
What is that ratio as in?
I means what is the magnitude? What is that? 131.6 or something else?
31.6 where? Here.
I took it as 131.6.
No, no, this is 1.6.
Yeah,
It's just
that
1. It's just
वो फिर
1.6.
13 जैसा लगा.
Okay, but you understand how it's done, right?
Yeah.
So that's important. Okay, let's move ahead to certain. Okay, right now, what we were talking about were systems which were in equilibrium. All that we've written right now, if even if there is a heat transfer such that in the first law, or even if you look back at the zeroth law, we were only talking about systems that were in equilibrium. So essentially, what does that mean? That means that if you want to draw a three-dimensional diagram, PV and T, so it's just a point in this three-dimensional space, and it just stays there. So उसका जो pressure है, उसका जो volume है, उसका temperature जो है, वो वही same ही रहता है, it never changes. So that is what one means by it's an equilibrium. But what if you want to study something that is actually not in equilibrium, it's actually changing. It's, let's say it goes from this value, which is, let's say, some pa va to some other value here, which let's say is pb vb and tb. Now, how does it go from here to here? There are many ways it can go from this point to here, this point, right? It can go along a path which has um, which has a constant volume, or it can go from a path which has constant pressure, or it can go from a path that has constant temperature. So that is essentially what we're going to do. We're going to divide the kinds of processes that can happen in such a way when it's going from one equilibrium to another equilibrium in such a way that all the states in between are also in equilibrium. So you can only study equilibrium things. So to study changes, what you do is you cut all these changes down into such small parts that in this small part the system is in equilibrium, and in this part the system is also in equilibrium, but a different equilibrium. So when it's going from here to here, it's going in small steps, and those small steps are essentially what one calls a quasi-static way of evolving things. Okay, so this is what is called a quasi-static
Uh,
process. So to study any change, essentially you're doing essentially the same thing that we did in calculus. If you go back to your calculus classes, when we were talking about differentiation and integration, what we essentially did was we had a curve, and we divided the curve into small bits, and we can assume that these small bits were straight lines. We're doing exactly the same thing here. We're assuming that this whole process is broken up into small things, and all these small things, we assume that there is an equilibrium. Okay, so essentially the system is going from one equilibrium to another equilibrium to another equilibrium until it reaches to the final state. Does that make sense?
Yes, sir.
Love.
So,
Huh.
so what have you written at the top?
At the top here,
Yes.
systems which were in equilibrium.
Sir, one more doubt, sir. You said that, sir, I mean, you said that at one time, if we're talking about two equilibrium, so one thing is in equilibrium, like either P or V or T. Is it not possible that all of these three are changing continuously?
Yes, they are changing, but you are doing the process so slowly that you can stay for some time and say that yes, this is an equilibrium. So essentially what you're doing, if you want to change the pressure from one atmosphere to two atmosphere, you first change it to 1.1, stay there for some time. You change it to 1.2, stay there for one time for some time. You change it to 1.3, and you keep on changing it until unless you get to 2. That is essentially what you're doing.
So one out of all these three has to be in equilibrium at some point of time.
No, all of them are in equilibrium. All of those states are equilibrium states in the sense that if one system is in that state, it will stay in equilibrium forever until unless some external work is not being done, some external heat is not being applied.
सर आप अपनी प्लीज पहली लाइन रिपीट कर दोगे द वेरी फर्स्ट लाइन यू सेड अबाउट व्हेन यू
I'm
आर
sorry.
sir can you please repeat the first line you said when you were drawing this diagram PVT.
First thing I said was every point here denotes a point of equilibrium, in the sense that if the system is has these conditions, let's PV and T, this PV and T, the system is not going anywhere from here. But if one wants to, like, if there is no heat provided or work is not done, but if you do some work or provide some heat, then the system goes to another point, which is going from A to B in this case, and that can go in many different ways. It can go along a line where the pressure is constant. It can go along the line where the temperature is constant. It can go along the line when the volume is constant, because two things are changing, right? So you can change two things in such a way that the third things remains a constant.
हाँ sir, so my question was this only, is it not possible to change all of these three things?
No, but you're making your life easier by doing that.
Okay sir.
Hello. Yes. Sorry, my internet just went away for some reason. Uh, okay. The host needs to make me. Okay. So what we were talking about. So what was the question? I'm sorry.
Yeah, the question was, can it not be possible that we're not changing, one thing is not constant and no wait, the question was,
No, that can obviously happen. That can also happen. Obviously, that can happen. No doubt about that. But it's just easier to analyze this.
okay sir.
And you'll understand it as we go ahead. Uh, just give me a second. Yes. Sorry. So where were we?
All of the three can change, you were saying.
All of the three can change. Absolutely, absolutely. So wait, I'm just trying to make myself host again because I cannot share screen otherwise. Yes, lovely. Okay. Yes, all the three can change again. Okay, we were talking about quasi-static process. So you understand what a quasi-static process is? Essentially a small process. Let's take an example of this, and I think that will make you understand this slightly better. Again, you have a gas inside, and you have some piston here, right? Now, if I'm decreasing the volume, what I can do is I can decreasing the volume really slowly, in the sense that my delta V is really small, so that I can write it as delta V dV. What else I can do is I can increase the pressure from outside. That I'm putting in the external pressure, P external. But I can also change that by some delta P, so that it again pushes inside. Or what I can do, I can increase the temperature by flowing some heat inside it, by some delta T. But I can do all of these things really slowly, such that every when it's changing from TA to TB, VPA, VA, PB, TB, such that it's going really slowly, and every single of these you can define some PV and T. You can define some PVP. That's the problem with not being in equilibrium, right? It is very difficult to even define what the pressure is and define what the volume is, because now it's changing. Now it's constantly changing. But in order to analyze something, you need small changes. Lovely. As I said, there can be many different kinds of changes. First of all, if we put temperature to constant, so we call it an isothermal process. If I'm going from a point to another point such that my temperature is a constant, in that case, I'll call it an isothermal process. If I keep the pressure as constant, what will I call it? I'll call it an isobaric process. Bar coming from the pressure unit bar, and a volume as a constant.
Isochoric.
I would say isochoric process. Is there some other thing that I can keep constant? Well,
Q.
what if I keep my heat as constant? As in the sense, I insulate it with an adiabatic wall, so that no heat is being transferred as well. But the pressure is changing, and hence the volume is changing, and the temperature is also changing. All three things are changing, but in a way such that the energy is not changing. You can also have a process in which the energy is also changing, and all of these three things are changing, but that is a very difficult thing to analyze, and because simply because it is not in equilibrium, and hence to define all these variables, it's very difficult. It's impossible essentially to do that. Q, we call it an adiabatic process. Okay, so we can keep these four things as constant. So obviously in this case delta T will be 0, obviously in this case delta P will be equal to 0, and obviously in this case delta V will be equal to 0, and here obviously delta Q will be equal to 0. Now let's go ahead and try to analyze each of these process in the sense that if I having these process, what is my first law
Sir,
says
sir,
about?
sir, I have a question.
Yes.
So for this adiabatic process, is the entropy constant throughout?
We've not yet come to entropy. एंट्रोपी की तो अभी हमने बात भी नहीं की है. एंट्रोपी इज अ डिफरेंट इशू. वील कम टू एंट्रोपी व्हेन वी डू.
Okay,
Okay,
okay, sir.
because there's a lot of things that we need to talk about there. Okay, so let's go one by one. Let's talk about the isothermal process. Well, what do you have in isothermal process? My delta T is equal to 0. If my delta T is equal to 0, what is my delta U? Any ideas? What is my delta U?
P delta V
Well, this is also
minus
equal to
tau.
0, right? Because delta U is just equal to C delta T. So my delta U is just 0. So my delta Q, if I'm providing, I mean, any kind of a change that is happening. So heat is being lost or heat is being gained, any kind of a process that is happening. My delta Q plus delta W, this is just 0, and this is just P delta V. So this is just equal to P delta V, which is essentially just the work done, delta W. Let's try to calculate what this P delta V is. Let's come to ideal gas again. So what do we have in ideal gas? We have PV is equal to nRT. Let's just take 1 mole of ideal gas, okay? Because why not? PV is equal to RT. Because we're talking about 1 mole. We know we can put in a mole whenever we want. We'll just absorb the value of the mole in this constant R. Okay. So, yes, P equal to RT. Okay, so what is my delta W now? Well, if my um, if my T is a constant, well then if I do a change variable here, we have P delta V plus V delta P is equal to 0, because my this is equal to delta T is 0, right? So what is my work done in this case? Any ideas? How do we proceed? How do we go ahead? Think.
Work done is minus V delta P.
Is P delta V? Yes. So minus V delta P, absolutely. So what one thing that we understood is P delta V is equal to V delta P. Absolutely, this is true. But let's say my delta V is so small, because now we're going and doing quasi-static process. So I can call it dV now. So my delta V is just P dV, the integral from whenever it changes from V1 to V2. So if let's say the volume is changing from V1 to V2, and the pressure is also changing from somewhere, from something to something else. Well, what is the value of pressure? Well, we can use this equation to get the value of pressure, which is just RT divided by V dV, which is, so my R is just a constant, and my T is also just a constant, because we're talking about an isothermal process. My RT can go out, and this is just dV by V, V1 to V2. What is the integral of 1 by V?
Log.
LNV.
So this is just RT log V from V1 to V2. So which is nothing but RT times log V2 divided by V1. So my work done for an ideal gas during an isothermal process is just the log of the ratios of the two change in volumes. Notice that this does not at all depend on pressure. We used the fact that there is an equation of state. So essentially, what was useful here was that first of all, we have three variables PVT, and since we were using the ideal gas, we could constrain the variables to just two variables, which in this case were P and V, and then using this using the first of all, we figured out that it's an isothermal process, so this is just a constant, and then because of this relation we can just reduce it to one variable, right? So essentially now everything, once you've figured out what the pressure is, you can figure out everything else in terms of the pressure, or in terms of the volume, or in terms of the temperature. One
So
thing you can need. So
so it can be written as RT ln P2 by P1 also, no?
by V2 by V1, yeah, that's
No,
P2 by
P2 by
P1.
P2 by
Uh,
P1.
yeah, initially, so if you think about it like this, the initially your state was P1 V1 is equal to RT, and P2 V2 is equal to RT.
मतलब
We can
P2 by
divide these two, and what we can get is P1 by P2 is equal to V2 by V1. Then yes, it's P1 by P2.
yes, sir.
So RT is RT log P1 by P2. So it's minus P2 by P1 essentially. Okay,
Yes,
lovely.
sir.
So this we were talking about an isothermal process. Let's talk about the adiabatic process first, because here what you have is something very interesting. Because here what you're saying is your Q, you're not providing any heat. Q is a constant. This implies my delta Q is equal to zero. So let's come back to our equation again. Delta Q is equal to delta U plus delta W. One is saying that this is zero. So what does that mean?
Del U equals minus W.
Yeah, 0 is equal to del U plus delta W. And we know what delta W is. This is just P delta V. Or we can write this as P dV now, because we've already talked about quasi-static process. So we can write this as P dV. And what is delta U? Well, depends on what process we're talking about, first of all. So what is delta U? Well, delta U is just C delta T, right? CV delta T, constant volume, yeah. CV delta T. So this is all CV dt. So what do you have? You have 0 is equal to CV dt plus P dV. So what does this mean?
So
Hmm.
so you're writing it as CVDT, matlab the volume is constant and the very next thing is P
No, no,
dV.
no, 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 no. No, 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 no. So when I was okay, so delta Q is equal to delta U plus P dV, right?
Yes, sir.
If my volume is constant in a process where if my volume is constant, so this term is zero. So my delta U is just delta Q, right?
Yes, sir.
So what does this mean? My CV is equal to delta U by delta T, because it's supposed to be delta Q by delta T, right? So since my delta U is delta Q, so this is delta U by delta T. So what does that mean? This means that delta U is CV dt, CV delta T. This is always equal to CV delta T. You don't need to. So you will have some CV for the gas, right? When I
Oh,
write CV here, this doesn't mean that my volume is constant.
okay, sir.
There, the gas itself, whatever gas this is, it will have some value of CV, right? And it will have some value of CV. So that is what I'm saying here. The value of CV, because this statement is true, I can write delta U as CV dt. Now we have again PV is equal to RT for 1 mole of the gas. So then what does this mean? This means that PdV plus VdP is equal to R dt, right? We're differentiating on both sides, keeping मैंने यहाँ पे कुछ गड़बड़ लिखा
इसमें
है.
वो माइनस नहीं होगा, माइनस आर डी टी.
Why minus?
या ओके ओके सॉरी, आई थॉट दैट वाज अ प्लस इन बिटवीन.
No, this is dp, vdp, right? Uh, okay, this is r dt, so dt. So what I can do is I can write this as dt is equal to p dv plus v dp divided by r, and I can use this to substitute inside here. And what will I get? I get cv by r, so cv by r times p dv plus v dp plus p dv. Okay, how to simplify this? Anybody? How to simplify this further? Any ideas? कुछ तो बताओ यार.
Integrating.
इंटीग्रेट तो करोगे, पहले लिखे को थोड़ा और सिंप्लीफाई कर दो जरा. डीवी डीवी को साथ में ले आओ. दैट इज वन वे टू सिंप्लीफाई इट, राइट? What do you have? You have cv by r multiplied by plus, okay, give me an eraser. You have plus 1 times p dv plus v dp, correct? Yes, no, maybe. कुछ तो बोलो यार. Okay. Okay, so what do we have here? We have 0 is equal to cv plus r by r divided by but you have a cv by r here also, right? Yes, because of this cv by r. यार मैं कुछ एरर कर रहा हूँ तो बताओ ना यार. If I'm making a mistakes, please be aware. Let me. Okay. Yes, you have PdV here plus CV by R. I cannot even write it here. Okay, I'm coming back up. 0 is equal to CV plus R divided by R multiplied by PdV plus CV by R multiplied by VdP. Now, now what else can we do? Well, we can realize that Cp minus Cv is just R, right? So I can just put in the value of R here in the numerator. So what do I get here? Cv plus Cp minus Cv divided by R times PdV plus Cv by R multiplied by VdP. Okay. What does this mean? This
So we
means,
could have cancelled the hours also.
well, your CV just gets cancelled, right? You can cancel out the R. We will cancel out the R soon. Okay, let's just cancel it out. You get CP here. So you get CP PdV plus CV VdP is equal to 0. Okay. Let's simplify this further. We can write this as what, dp divided by p plus cp divided by cv times dv divided by v is equal to 0. We can call this ratio as some gamma. Okay. So gamma is equal to Cp by Cv. Let's call this ratio this thing called gamma. So this is just dp by p plus gamma dv by v is equal to 0. Now let's integrate on both sides. What do you get? Anybody? We've already done this. This is just log p plus gamma log v is equal to 0, right? Is equal to 0. Is this correct or is this wrong? Any ideas? कुछ तो बोलो यार.
सही लग रहा है फिलहाल तो.
सही लग रहा है. सही कैसे लग रहा है? यहाँ पे इंटीग्रेट किया तो कांस्टेंट तो आना चाहिए ना कहीं. So you'll have a constant here rather than being a 0. You've integrated, so there's a constant here.
सर कैन यू प्लीज एक्सप्लेन ये कांस्टेंट कहाँ से है?
अरे integrate करते हो, so you get a constant of integration, right? So integral of dp by p is log p plus a constant. Integration of dv by v is log v plus a constant. सारे constant को इकट्ठा करके मैंने right hand side पे डाल दिया. Okay? And called it a bigger constant. Capital C.
सर तो इससे पहले जब हमने इंटीग्रेशन किया तब हमने कोई कांस्टेंट क्यों नहीं डाला?
क्योंकि वहां पे हमारे पास लिमिट्स थी ना, v1 और v2. यहाँ पे लिमिट्स नहीं है.
अच्छा ओके ओके यस आई गॉट सर.
Lovely, lovely, lovely. So, using log properties, what do you have? V to the power gamma is equal to a constant. This implies PV to the power gamma is equal to a constant. So, for an adiabatic process, what you have, what the relation that you have is that PV to the power gamma. Gamma is this constant, Cp by Cv is actually a constant. So what does that mean? That means if I am starting with a situation A, P A V A, and I'm going to P B V B, but I'm going through an adiabatic process in the sense that there is no heat that is being either put in or pumped out. Heat is remains a constant. So what would you have? You have PA VA to the power gamma should be equal to PB VB to the power gamma. And not only that, the whole process that I'm going through, if I'm going from A to B through this process, every single point here, every single state here, PV will also obey PV to the power gamma is equal to a constant. Will be equal to all the PIVI to the power gamma. Let's call this PIVI. Does that make sense? So this is a adiabatic process is a very, very particular process in which your pressure multiplied by the volume to the power gamma is a constant. And why is it a constant? We just derived why it is a constant. Let's try to write this relations in some other form. PV to the power gamma is equal to constant. Well, we know that PV is equal to RT. So one thing I can do is just write P is equal to RT divided by V and just substitute it back. What do I get here? We get RT divided by V. V to the power gamma is equal to constant. R is also a constant, so I can just take it on the other side and absorb it into the constant, right? So this is T to the power V gamma minus 1 is equal to a constant. This is another relation that one can think of. And the third thing that you can have, so you have PV and T, so you can have PV relation, you can have PT relation, and you can have VT relations. So this is the VT relation, and this is the PV relation. And the third one would be the PT relation if we substitute V from this equation here. So what would that entail? This implies that V is equal to RT divided by P. Let's substitute it back. What do you have? You have P RT divided by P to the power gamma is equal to a constant. This would imply that P 1 minus gamma, R to the power gamma, I can take it to the other side and absorb it into the same constant. and T to the power gamma is equal to constant. So this is the relationship between T and P. So this is how one defines an adiabatic process. Let's think about what is the work done in such a process. Well, work done is defined just by P delta V, right? Delta W is just P dV, right? And I've already told you that PV to the power gamma is a constant. Let's call this constant a capital C. So what essentially you have P is equal to V divided by this constant divided by V to the power gamma. Substitute back inside. So your integral from, if you are going from V1 to V2, C divided by V to the power gamma dV. What is the integral of 1 by V to the power gamma? How do you integrate this? कोई बता सकता है?
lnv to the power gamma.
नहीं, V to the power gamma. So
अच्छा
this
सर,
is
तो
essentially
v to
V
the
to the
power
power minus gamma dV, right?
यस सर, इसके बाद इंटीग्रेशन करेंगे.
So what is the value of this?
जस्ट अ सेकंड सर.
This is just V. इतना टाइम नहीं लगना चाहिए. When you
माइनस
integrate,
r प्लस 1 अपॉन माइनस 1 प्लस हाफ.
lovely. So essentially, what do you have here? This constant is there. You have V to the power 1 minus gamma divided by 1 minus gamma from V1 to V2, which is just equal to C divided by 1 minus gamma times V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma. So this is essentially the work done, where C you can just calculate from putting in P1 V1 to the power gamma. So essentially this is just P1 V1 to the power gamma divided by 1 minus gamma, V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma. Work done in a adiabatic process. Realize that what we're doing is exactly the same thing throughout. Now let's move on to the remaining processes. First of them were isochoric.
So can you please show that equation of work again?
Can you repeat that?
Work of an adiabatic process.
See, work done is just PdV, right? And I've told you in an adiabatic process, PV to the power gamma is a constant. So बस P की वैल्यू यहाँ से उठाई, यहाँ पे डाली and integrate कर दिया. Once I integrate it, what do I get? You get some constant divided by 1 minus gamma v to the power 1 minus gamma from V1 to V2. This is what you get after you integrate. And this constant is essentially this constant, which is PV to the power gamma. So in this process, when it's going from P1 V1 to P2 V2, this thing PV to the power gamma should be a constant. So I can pick P1 V1 to the power gamma or P2 V2 to the power gamma as C, anything I want. I just pick P1 V1 to the power gamma minus gamma V to the power 1 minus gamma minus V1 to the power 1 minus gamma. Make sense? Yes, no, maybe?
Yes, sir.
Lovely. Okay, let's we talked about let's talk about isochoric. What does isochoric mean? Well, it means volume is a constant, so this implies delta V is equal to 0. Let's go back to our beautiful equation. Delta U plus P delta V. Delta V is 0, so this is 0. So my delta Q is just CV dt. Now, yeah, so if the temperature is going up from T1 to T2, this is just equal to CV T2 minus T1. As simple as that. And what is the work done in such a process? What is the work done? बताओ बताओ जल्दी बताओ, व्हाट इज द वर्क डन?
Zero.
Zero. Very nice. Lovely. Because your volume is not changing, so PdV is equal to zero. Lovely. That was isochoric, isobaric. What do you have? You have pressure, which is a constant. So delta P is equal to zero. Again, delta Q is equal to CV dt plus PdV. Correct? So my pressure is a constant. What the relation do we have? We have PV is equal to RT because we're talking about an ideal gas. Always talk about an ideal gas. Um, so PdV, so PdV is just equal to RDT, correct? So just put it here. You have CV dt plus RDT, which is equal to CV plus R dt, which is nothing but since R is also equal to Cp minus Cv, so my Cv plus Cp minus Cv times dt, these two cancel out, which makes it Cp dt. Integrate this, what do you get? Get Cp T2 minus T1. So the energy put in will just be equal to your Cp and the change in temperature. As simple as that. What about the work done? What about the work done? Well, work done is just equal to PdV, and well, you can just integrate this and just say P V2 minus V1, or you can be fancy and be like PV is equal to RT. So my PdV is equal to RDT. So this thing is also equal to an integral over R dt, which is nothing but R t2 minus t1. Okay, so my energy is going up by R, sorry, Cp delta T, and my work done is going up by R delta T. This is in an isobaric process. Okay, everything clear till here? चलो अब क्वेश्चन करते हैं, देखते हैं कितना क्लियर है. Okay, wait. Before that, let's try to plot these things. So isothermal, you have isobaric, and you have isochoric, and you have adiabatic. So if we want to plot our PV diagrams as we did, so my pressure is changing from P1 V1 to some P2 V2, but I'm saying it's going through an isothermal process. So how would this look like? Well, since PV is equal to constant, because PV is equal to nRT, and T is a constant, because T is a constant. So nRT itself is a constant. So PV is a constant. Since PV is a constant, so P is equal to some constant divided by V. How does this graph look like? Any ideas? This looks
Say
like
what
a,
repeat again. Sir, will you please repeat?
what does this graph look like? PV is equal to a constant. What does this graph look like? For an isothermal process, my T is a constant. So my nRT is a constant. Hence my PV is a constant. Since PV is constant, what does this PV is equal to constant? Graph कैसे लगता है? XY is equal to 1. What does this graph look like? A
Hyperbola.
hyperbola, absolutely. So essentially this curve, this is a hyperbolic curve. and with the equation PV is equal to whatever constant you have. Constant की value आप निकाल सकते हो अगर आप P1 V1 पता है तो P1 V1 to the power gamma करके आप इस constant की value निकाल सकते हो. Yes. No, that is adiabatic, sorry. You can just put in the value of temperature here, whatever temperature it is in this nRT, and calculate the constant. But the fact is that it's a hyperbola. What about an isobaric process? Well, isobaric process means my pressure is constant. If my pressure is constant, then this will just be a straight line. What about isochoric? Well, isochoric, since my volume is constant, it will be a straight vertical line. But what about an adiabatic process? If I'm going from P1 V1 to P2 V2, what equation does that follow? This follows PV is equal to constant. This follows P is equal to 0. This follows V is equal to 0. And this follows PV to the power gamma is equal to constant, which essentially is a very similar graph which looks like this, but is not exactly the same. So let's say the upper one is a hyperbola and the niche one is the PV to the power gamma is equal to constant, because upper wala is PV is equal to constant. Not exactly the same because the fall is steeper because gamma is greater than 1. So the fall is steeper. So these are the three different kinds of graphs that the four different kinds of processes and how they essentially look like in a graph. Okay, let's do this question here. Okay. If at 50 degrees Celsius and 75 centimeter of mercury pressure, a definite mass of a gas is compressed, first of all slowly, दूसरी बार suddenly, then what will be the final pressure and temperature of the gas in each case if the final volume is 1/4 of the initial volume. Do I have to give you something else? I have to give you gamma. Question mark. Gamma is equal to 1.5. So if at 50 degrees Celsius and 75 centimeter of mercury pressure, so centimeters of mercury is also a unit of pressure that one uses other than bar and Pascal. A definite mass of a gas is compressed. So let's say some mass M is compressed, first of all slowly and secondly suddenly. What is the difference between the two? When one says slowly, one means quasi-static. And one says suddenly, one means adiabatic. No heat is being put in. If you do it very quickly, there isn't enough time for heat to flow inside or out. Right. So what will be the final pressure and temperature of the gas in each case? Any thoughts? Quick problem? Okay, so I think um, we can stop here. How about you guys take this question home, solve it, and we'll discuss it first thing next class. We've gone through the first law completely, and yeah, these are the things that one needs to understand. That's it. Okay, any questions, Abhitak? No? Okay, lovely. Okay, so I think you can leave and we can talk next.